The resonance. First of all, see the definition. So resonance is the steady state operation of a circuit at a frequency for which the response is in time phase with the source function. Despite the presence of energy storing elements. So resonance is defined as the steady state operation of a circuit at a particular frequency for which the circuit response is in time phase with the source function despite the presence of energy storing elements. Let's elaborate this definition. The energy storing elements are the inductor and the capacitor. As we have already seen that the inductor can store the energy, electrical energy, in the form of magnetic field, and capacitor can store the electrical energy in form of static charges. So in definition it is states that if in a electrical circuit the energy storing elements, that means inductor and capacitors, are present, then at a particular frequency the response of the circuit, here response means the current, is in time phase with the source function. The source function means the supply voltage. So in simple word, despite the presence of inductor and capacitor, if current and voltage are in phase, inductor and capacitor are present in the circuit, then if the current and voltage are in phase, then this situation is considered as the resonance. And the frequency for which the voltage and currents are in phase, this frequency is considered as resonant frequency. This is called the resonant frequency. Now we know that the inductor and capacitors may be connected in series or they may be connected in parallel. So the resonance can be occurred only if inductor and capacitor both are present in the circuit. Remember one thing, only inductor or only capacitor cannot create resonance. So to create the resonance, both inductor and capacitor should be present in the circuit. And as we have stated that the inductor and capacitors may be connected in series and they may be connected in parallel. Therefore, according to their connections, The resonance is of two types. So the first one is called the series resonance, and the second is called parallel resonance. So let's discuss the series resonance and parallel resonance one by one. The series resonance. Here we have considered a series RLC circuit where a resistor, an inductor and a capacitor are connected in series. Across the supply voltage V and the current flowing in the circuit is I. Here the frequency is F and this frequency can be changed. We know that the XL, that is the inductive reactance, is represented as 2 pi FL, and the capacitive reactance XC is represented as 1 upon 2 pi FC. So therefore the total impedance of the circuit Z is square root of R square plus XL minus XC whole square. This we have already discussed in previous classes when RLC series circuit has been discussed. Now here, if we draw the phasor diagram with respect to the current, so here we can see that the current is taken as a reference. The voltage drop across the resistor, that is VR, it should be in phase with the current. The voltage drop across the inductor and across the capacitor, VL and VC. So VL will be leading the current by 90 degree and VC will be lagging the current by 90 degree. So during RLC series circuit analysis, we have seen that there may be three conditions arises. Here the VL is I into XL, VR is I into R, and VC is I into XC. That we have already discussed. So there may be three conditions arises. Either XL is greater than XC, so VL will be greater than VC, or XL is less than XC, so VL will be less than VC. And the third condition was when XL is equal to XC, then the VL will be equal to VC. So we have already seen the voltage equation, and it was square root of VR square plus VL minus VC whole square. So if XL is equal to XC, therefore VL will be equal to VC. So this term will become 0, and we can say that the V will be equal to VR when VL is equal to VC, that is XL equal to XC. So in a RLC series circuit, the voltage drop across each elements VL, VR and VC are given here, where XL is equal to 2 pi FL, XC equal to 1 upon 2 pi FC. From the relations of the voltage, we can see that V is equal to square root of V square plus VL minus VC whole square. And if XL is equal to XC, then VL will be equal to VC. Therefore, V will be equal to VR. And VR is the voltage drop across the resistance. It will be equal to the supply voltage. and then it will be in phase with the current. That means the phase angle between voltage and the current will be 0. Therefore, the power factor will be equal to 1. Now, from these two relations, we can say that when the frequency f is equal to 0, then XL will be equal to 0 and XC will be equal to infinity. That we can see from these two relations. As the frequency is gradually increasing, then the value of the XL will be gradually increasing, but the value of XC will be gradually decreasing. And when the frequency is infinity, then the XL will be infinity and XC will be equal to 0. So as the frequency is gradually increasing, the value of XL will be gradually increasing, but the value of XC will be gradually decreasing. So there may be a particular frequency, let's say FR. At this frequency, let's say at FR, let's say XL will be equal to XC. So now we can write XL is equal to 2 pi FRL, because now the frequency is FR, and it will be equal to XC, that is 1 upon 2 pi FRC. From these relations we can write FR square is equal to 1 upon 2 pi square into LC. So finally we can write FR is equal to 1 upon 2 pi root LC. So this is the resonant frequency of a series RLC circuit. That means if the frequency is equal to this value, then the value of XL will be equal to XC, the net reactance will be 0, and the voltage of the supply voltage and the circuit current will be in phase, and then the power factor will be equal to 1. From this relation we can also write 2 pi FR is equal to 1 upon root LC. So from there we can write omega R is equal to 1 upon root LC. Let's see the important points about the series resonance. Assume the circuit RLC series circuit is running with a supply voltage V, and the frequency of the supply voltage is equal to the resonant frequency, where FR is equal to 1 upon 2 pi root LC. So in this case, at resonant frequency, XL should be equal to XC. That is the condition for resonance for a series circuit. So as the XL is equal to XC, then Z of a series RLC circuit, we know that Z is equal to square root of R square plus XL minus XC whole square. So at resonance condition, the Z should be equal to R, because XL is equal to XC. And as the XL is equal to XC, therefore the voltage drop across the inductance should be equal to the voltage drop across the capacitance. So the supply voltage of a series RLC circuit, which is given by VR square plus VL minus VC whole square, here the supply voltage should be equal to the voltage drop across the resistance. So as the voltage drop across the resistance is equal to the supply voltage, therefore the phase angle, that is phi, should be equal to 0 degree. Phase angle between voltage and current should be 0 degree. Phase angle between V and I. Remember here V is equal to VR. So as the phase angle is 0, therefore the power factor of the circuit will be 1. And in this case, the power of the circuit, the active power, is Vi cos phi. Here the power will be the maximum. It should be V into I. The current in the circuit, as we know that the current is equal to V upon Z. So in resonance condition, as the Z is equal to R, that is the minimum, so the current will be maximum and it will be V upon R. Because at resonance condition we have already seen that the impedance is equal to R, that is the impedance is minimum. So as the impedance is minimum, therefore the current will be maximum. And as the current is maximum, that means the circuit allowed to flow the maximum current, then this circuit is also considered as a current acceptor circuit. Or simply acceptor circuit. So if we summarize this, in a RLC series circuit at resonant frequency, the inductive reactance will be equal to the capacitive reactance. Therefore, the net reactance will be equal to 0, that is XL minus XC. And as the net reactance is 0, therefore the impedance will be minimum and that will be equal to R. And as the XL is equal to XC, therefore VL will be equal to VC. Therefore, the supply voltage will be equal to the voltage drop across the resistor. And so the phase angle between the supply voltage and the circuit current will be 0. As a result, the power factor of the circuit will be unity. So the maximum amount of power will be transferred to the load and it will be equal to V into I only. During resonance, as the impedance is minimum, so the current will be maximum. So it will be V upon R. And as the maximum current flow through the circuit, then it is also considered as the acceptor circuit. Let's see the graphical representation of resonance in a series RLC circuit. Here we will analyze the series RLC circuit with respect to the frequency, and we will also identify the resonance frequency and the behavior of the circuit at resonant frequency. So in the graph we have taken frequency as the reference and we will check each and every parameter with respect to the frequency. So first of all, the resistance. As we know that the resistance does not depend upon the frequency. Therefore, if the frequency is gradually increased, then the resistance of the circuit will be constant. So there will be no change in the resistance. So the resistance characteristics will be a straight line parallel to the frequency line. Next is the inductive reactance XL, that is 2 pi FL. So from this relation we can see that as the frequency increases, then the XL, that is the inductive reactance, will also be increasing. Therefore, the characteristics of the XL will be a straight line passing through the origin. So this is the characteristics of the inductive reactance. Next is Xc. We know that Xc is equal to 1 upon 2 pi Fc. And if the frequency increases, then the value of Xc will be decreased. Here remember, the Xc is always considered as the opposite of XL. So if XL is drawn in the first quadrant, taken as positive, so Xc will be drawn in the fourth quadrant and it will be considered as the negative parameter. So the nature of the capacitive reactance will be a rectangular hyperbola in the fourth quadrant. That means when the frequency is very low, or it is 0, the Xc is almost infinity. And as the frequency is gradually increasing, then the capacitive reactance will be gradually decreasing. So this is the nature of the Xc. Next is X, that is the net reactance, and it will be the difference of XL and Xc. So from this graph we can see that when the frequency is lower, then the capacitive reactance will be more than the inductive reactance. Therefore, the difference of XL and Xc will be capacitive in nature. So it will start from the fourth quadrant. And as the frequency is gradually increasing, then the XL will be increasing but the Xc will be decreasing. Therefore, the X, that is the net reactance, will be gradually decreasing. At a particular frequency, we can see that the net reactance will be 0. And this is considered as the resonant frequency, because we have already seen that at resonant frequency, the XL will be equal to Xc. So here we can consider that if the frequency is lower than the resonant frequency, that means from 0 to Fr, here the Xc will be greater than XL, so the circuit nature will be resistive capacitive. So if the frequency is lower than the resonant frequency, the Xc will be greater than XL, so the circuit behavior will be resistive capacitive. At resonant frequency, both XL and Xc will be equal, so the circuit will be purely resistive at resonant frequency. But after the resonant frequency, now XL will be greater than Xc, so the nature of the circuit will be inductive. That means here XL will be greater than Xc and the circuit nature will be resistive inductive. The next part is the impedance, and it is the square root of R square plus XL minus Xc whole square, or we can say X square, where X is the net reactance. Here R is the constant. So at lower frequency, the value of X is very high because the capacitive reactance is very high. Therefore, the impedance will be maximum. But as the frequency is increases, the difference between XL and Xc will be reduced. So X will be reduced. Therefore, the Z will also be reduced. At resonant frequency, X will be equal to 0. So Z will be equal to R. And after the resonant frequency, XL will be now more than X. So X will be again increasing. Therefore, the Z will also be increasing. So the nature of the impedance can be like this. So this is the impedance of the RLC series circuit. So here we can see that at lower frequency the impedance is very high. If the frequency is gradually increases, the impedance will be reduced. At resonant frequency, the impedance will be equal to R. And after the resonant frequency, the impedance will be further increased. And finally, the current. As we know that the current is equal to V upon Z. So when the Z is maximum, the current will be minimum. And as the impedance is gradually decreasing, therefore the current will be gradually increasing. At resonant frequency, the impedance is minimum and that is equal to R. Therefore, the current will be here maximum. After the resonant frequency, impedance further increases. So, the current will be again in the decreasing order. So, the nature of the current will be like this. So, this is the characteristics of the current with respect to the frequency. So this is a complete graphical representation of a series RLC circuit, and here we can see that at resonant frequency XL is equal to XC, so the net reactance is 0, so the impedance is minimum, that is equal to R, and hence the current is maximum and that is equal to V upon R. Now from the graphical representation of the series resonance, if I see the nature of the current with respect to the frequency, and if we draw it separately, it will be look like this. So this is the current in a RLC series circuit that changes with respect to the frequency. When the frequency is low, the current will be low. As the frequency is gradually increasing, the current will also be increasing. When the frequency is equal to the resonant frequency, the current will become maximum. After the resonant frequency, if the frequency increases further, then the current will be decreasing. Here the curve of the current with respect to the frequency is called as the resonance curve. In the resonance curve, we can see that the maximum current Imax, and this Imax is equal to V upon R, because at resonant frequency, the impedance is equal to R. Therefore, the current will be V upon R, because the value of impedance is equal to resistance. So the maximum current that we will obtain at resonant frequency will depend upon the resistance. Therefore, if the resistance is increased, then the peak value of the current will be decreased. So let's say this is for resistance R1. We take another resistance R2, and if R2 is greater than R1, then for R2 the nature of the current with respect to the frequency will be this. So this is the nature of the current in a RLC series circuit when the resistance is equal to R2, where R2 is greater than R1. If we take another resistance R3, which is further greater than R2, then the nature of the current will be like this. So this is the resonance curve for the resistance R3. So here we can see that the sharpness of the curve will be gradually decreasing if we increase the value of the resistance. This is represented by a term called selectivity. This is called the selectivity of the circuit. That means if the resistance is low, then the current will be very high, so it will be considered as a highly selective circuit. So for low resistance, the circuit will be highly selective. And for high resistance, if the resistance is increased in a RLC series circuit, then the sharpness of the curve will be gradually flattened. So this is called low selectivity. This is called highly selective circuit, and this is called low selective circuit or low selectivity. This resonance curve will be further used to describe the bandwidth that we will discuss in the next class. Thank you.